So the next step that will take us to the form you're more familiar with just requires taking the material time derivative of both sides of this equation. So we're just going to say that d dt, and I'm going to drop the explicit dependence on the intermediate variables now, because as you'll see shortly, it's not going to become as important. But we know that the density 0 is just a function of big X, right? Rho 0. Same phi 0, right? And that must equal to the material time derivative, okay, of the other side, which is rho phi j. Okay. Well, because the density, the initial reference density and the initial reference porosity aren't in any way functions of time. They're, by definition, they're the reference values. Then the left-hand side is identically 0. Right? And so this is why it's not as important to carry around the intermediate dependence on the variables at this point, because now all we're left with is d dt of the current density, the current porosity, and J, right, which is the determinant of that tensor F, which is this variable transformation between the current and reference configuration. Right? And so we'll just use the chain rule, and I'm going to keep the rho and phi together, so we'll have d dt rho phi j plus rho phi d dt j, right? And then I'll go ahead and use my definition of the material time derivative on this first term. I'll pull the j out here and leave it alone. And then we just have partial rho phi partial t plus the gradient of rho phi times v plus rho phi d dt j. So to figure out what d dt of j is, I'm going to start a new page and we'll come back to this. So d dt j, right, is, remember, d dt times the determinant of that matrix F. And I'm going to switch to using what we'll call indicial notation. And I'll kind of explain what I'm doing along the way, but we already said that we had that, F, the component Fij is just simply partial x, partial xi, partial big X j. Recall when I write this that little x is a function of big X. Right? It sort of has to be, otherwise that expression doesn't make sense. It's like you're taking the partial of a independent variable with respect to an independent variable, right? Which doesn't make sense. Here, little x is dependent on big X. Okay. So just keeping that notation in mind, we'll move into the next steps. Okay. Now there's an identity in, well, I guess first of all, what we're going to do is just we're going to use the chain rule here, right? Because f is a function of time, because f is a function of little x, which is a function of time, right? What we'll do is we'll just apply the chain rule here. And so what we're going to say is that the partial the determinant of F with respect to its components times like that, right? So that was nothing but the application of the chain rule. Now, there's an identity, and we're not going to prove it here. We're just going to use it. You could look it up in sort of any linear algebra text, that the partial of the determinant of a matrix with respect to its components is equal to the determinant of the matrix times the transpose inverse of the matrix. So in this indicial notation, this would be Fji, right? That's the transpose of F times its inverse, right? Or the inverse of that. Right? So just the partial of the determinant of a matrix with respect to its components is equal to that. That's just an identity that's common. Right? And so just for completeness, we'll write this term here. Okay. So remember, the determinant of F is just J. Right? And now I'm going to write out, it'll prove useful in a moment to write out F in terms of, write out this F transpose inverse in terms of our definition of F, right? In terms of, F is the partial xi partial xj. So in case of that, its inverse transpose is partial x I partial little x j. Right? So that's all that is. Okay. And we'll do the same thing here, right? So we're going to write out F in terms of its definition, right? So we have partial t partial little x I partial x j. So now we can just switch the order of integration on the last term. So I have j partial xi partial xj. Switch the order of integration so that I have partial x j partial xi partial t. Well, partial xi partial t, right, that's the time derivative of the position vector, which is we typically call the velocity, right? So we'll say that that's partial vi, right, the velocity vector. Now we've just replaced this with vi, right, partial xj. And then we can rearrange this term to be partial vi partial xj partial xi partial xj. Okay. Now, so this is the partial derivative of something, of the ith component with respect to itself and the jth component. So let's if I have if I have a function that's equal to x, right, and I take the derivative of that function with respect to x, then that's just like partial x, which we know is 1. Right? So in this case, I'm not doing anything more than that, except I'm doing it component by component in the tensor, right, or I'm sorry, in the matrix in this case. I'm not ready to sort of introduce you to tensors yet. We'll just call this a matrix still. And so what that turns out to be is the identity matrix, and in this indicial notation, we label the identity matrix as Fi as delta ij. Right? And so what delta ij is in the case of 3 by 3 matrices, it kind of plays the role of an identity matrix, but what it really is something called a Kronecker delta function. And it simply takes on a value of 1 when I equals to j and 0 otherwise. And so with that logic in hand, we can use this Kronecker delta function to switch the indices of one of these, of one of the two, and it doesn't matter which one, but of one of the two, either the I or the J here, to eliminate, to get rid of the Kronecker delta right there. So in other words, what we'll do is say that this is VI partial XI. And what you're more commonly used to seeing this as, partial VI partial XJ, is as a gradient operator. So we have the J, as a divergence operator. So we have that J is equal to the divergence of V. And where that comes from, right, the divergence operator, so I'm just going to go up here. This nabla operator, or the gradient operator, it's like a vector, right? So it's like a vector that's like partial x1, comma, partial x2, comma, partial x3. Right? And so then, of course, if V has components V1, V2, V3, then this gradient operator dot product V is going to give you partial V1, partial X1 plus partial V2, partial X2 plus partial V3, partial X3. Okay? And so right there, you can see that whenever you have this repeated indice, right? So if I have in this indicial notation, it was kind of obvious when I started because I was dealing with like matrix product operations. But here, wherever you have this repeated indice in a term, okay, this is like the summation, okay? So in other words, whenever you see partial VI, partial XI, this is like the summation from where I goes from 1 to 3 in this case of, partial VI, partial XI. And so anytime you see a repeated indice, in this case the I is repeated in the term, then it's just implicit, there's an implicit summation over that. And this idea or this notation was introduced by Einstein. So this is Einstein notation, or Einstein indicial notation. Okay. So again, now we know what dt of J is. We can go back to our conservation of mass equation and make that substitution. Right? And so we have that J Okay. Now, remember, all this is equal to 0, so I can divide through by J, canceling those terms. And then you should be able to see from the product rule that that term is simply equivalent to this. Right? If you just use the product rule of this guy, then you get that. And so then finally, we have our final kind of statement of conservation of mass in the form that you're probably familiar with. equal to that. That's equal to 0. So this is the fully three-dimensional conservation of mass equation. We didn't have to talk about Reynolds transport theorem at all. We just needed the knowledge of essentially the material time derivative, this notion of a control mass, that is a fixed mass that we're going to follow through some motion, and vector calculus, and you can derive the equation. Now, just for completeness, I will write out what the individual components are. Right, so we had that divergence operator there, right? So we have to write it out completely for that. And if you sort of prefer a more engineering notation, then you can just make the substitutions that x1 is x, x2 is y, and x3 is z. Right? Then you have that's quite possibly how you're more used to seeing it. Again, conservation of mass.